Don't hate me because I'm better than you. Respect me for what I can teach you. Okay, first of all, I would respect you a lot more if you would not spout such douchey nonsense like that. Also, those two things aren't mutually exclusive. You can respect and hate somebody at the same time. Trust me, I know. I went to the University of North Carolina. I will admit that Mike is one of the greatest coaches in college basketball history. That being said, I would not shed a single tear if he was involved in a single car, non-fatal car accident. Non-fatal, not a monster. So in general, when we talk a little bit about acids and bases, just a little, really nothing beyond acid plus base gives you salt and water. But in general, too, we start talking about acid-base chemistry in a little more detail. And we usually start by going back and redefining what it means to be an acid or a base. Back in General 1, you were probably just taught what we call the Arrhenius Definition, which defines acid-base behavior by what happens when you dissolve it in water. So an Arrhenius acid is defined as something that dissolves in water to produce hydrogen ion. For example, you take hydrogen chloride, put it in water, it'll dissociate like an ionic compound to give you hydrogen ion and chloride ion. Sorta, kinda. See, hydrogen ion doesn't technically exist in water. What really happens is that hydrogen chloride is reacting with at least one water molecule to give you a polyatomic ion called hydronium and chloride ion. So a more technically correct modernized way to define an Arrhenius acid is something that dissolves in water to produce hydronium. An Arrhenius base is defined as something that dissolves in water to give you hydroxide ion. So the most common type of base you typically run into are metal hydroxides like sodium hydroxide. It's an ionic compound, so it'll dissociate to give you the cation, sodium in this case, and hydroxide. But another base you run into in Gen Chem is ammonia, and it's a base because it'll react with water kind of like hydrogen chloride did earlier to give you ammonium ion and hydroxide. So again, hydroxide is produced, so Arrhenius would call that a base. But as you get deeper into chemistry, even though the Arrhenius definition works fine in Gen Chem, as you get deeper into chemistry, you'll see that the Arrhenius definition has one big limitation, and that is only defining what happens in aqueous solution, when water is the solvent. But as you get into things like organic chemistry, you'll see that there are other types of reaction solvents besides just water. And once you start using other solvents, the Arrhenius definition is pretty much useless. So a couple of guys who thought about this are Brønsted and Lowry, independent of each other. And they both came up with a definition based on the transfer of what we call a proton, which is really just hydrogen ion. Even though I just said hydrogen ion doesn't technically exist, we still sometimes think about it that way. Because 99.9%, remember, of hydrogen is hydrogen 1, a proton and a new electron. You take away the electron, all you're left with is a proton. So Brønsted and Lowry defined an acid as a chemical that donated a proton to something else. So you go back and look at the hydrogen chloride reaction, the more technically correct one, you can kind of think through that reaction as the hydrogen chloride donating a proton to water to give you hydronium and chloride. So in this case, hydrogen chloride would be an acid, just like before. And looking at the, as far as bases are concerned, they define bases as a proton acceptor. Like in the ammonia water reaction, ammonia can be viewed as having accepted a proton from water to give you ammonium and hydroxide, and that would make ammonia a base, just like before. And you're probably thinking, well, if it's just like before, why bother? But Brønsted-Lowry's definition kind of broadens the idea of what an acid or base can be. I mean, you look at these two reactions. Before, water was just a solvent, but hydrogen chloride is donating the proton to water. So that makes water a base. It's accepting that proton. And in the ammonia water reaction, ammonia is accepting a proton from water. So water is donating the proton. That makes it an acid. So in the Arrhenius definition, water was just a solvent, but here it's acting like an acid or base. And there are a lot of chemicals that can do both, kind of like water is doing here. And the term we use is amphoteric. Amphoteric means it can be a Brønsted acid or a Brønsted base. Another example you'll sometimes see is hydrogen phosphate. If you react hydrogen phosphate with ammonia, you get ammonium and phosphate. So in this reaction, hydrogen is donating the proton to ammonia, making it the acid, and ammonia is the base, like before. If you react ammonia or hydrogen phosphate with hydrochloric acid, hydrochloric acid is donating the proton. So in this case, hydrogen phosphate's accepting it, making it a base, and again, hydrogen chloride's the acid. And you'll notice in these reactions that you see things sort of happening in sort of pairs. Whenever ammonia accepts a proton, you're going to get ammonium. Whenever hydrogen chloride donates a proton, you're going to get chloride. So these are what we call conjugate pairs. And conjugate pairs are defined as two chemicals that relate by the loss or gain of a proton. They differ by, just one proton, or again, H+. So for example, in the ammonium water reaction, ammonium and ammonia are conjugate pairs. Water and hydroxide are conjugate pairs. In the hydrogen chloride reaction, hydrogen chloride and chloride are conjugate pairs. Water and hydronium are conjugate pairs. But just because water and hydroxide are conjugate pairs and water and ammonium are conjugate pairs doesn't mean that hydroxide and ammonia or hydroxide and hydronium are conjugate pairs. Again, they differ by two, and conjugate pairs are defined by being different by just one proton. Because just because they both are conjugates with one thing doesn't mean they're conjugates with each other. Again, it's the loss or gain of one proton. So there's actually a third way you can define what an acid or base is. And this was the definition that was sort of coined by Lewis, who you may remember from his structures. And Lewis was one of the first guys to figure out how bonding worked and what a covalent bond was. And as he started to look at this stuff, he realized that the proton transfer thing, it works fine, but chemical reactions don't really happen by protons transferring. Protons are in the nucleus. Chemical reactions, most of them, happen through electrons, redox reactions, covalent bonds being formed, sharing electrons. So he decided to come up with a more technically correct way to define acids, which we call Lewis acids and bases, by the transfer of an electron. So an acid, by Lewis's definition, isn't a proton donor, it's an electron acceptor. So again, looking back at the hydrogen chloride water reaction, Brønsted defined it as a proton being transferred to water. But Lewis said what really happens is that water is donating electrons to hydrogen, and it's breaking that bond with chlorine to give you chloride and hydronium. Likewise, a base, instead of being a proton donor, Lewis defined it as an proton donor. No, I got them flipped. Proton acceptor. I'm trying to look at one thing and say the other thing. Lewis defined bases as electron donors. Going back to the Brønsted-Lowry definition. Brønsted and Lowry they defined that reaction as water donating a proton to ammonia. But Lewis said what's really happening is that ammonia is donating electrons to hydrogen. That bond's being broken because hydrogen likes ammonia's lone pair instead of the shared pair it currently has to give you ammonium and hydroxide. By the way, if you are going to take organic chemistry, you kind of see what I'm doing with the arrows for the Lewis definition. You'll be doing that a lot next year probably. But again, everything that was an acid before is still an acid. But kind of like Brønsted and Lowry defined the definition of an acid from Arrhenius, Lewis kind of expands it even more. So, for example, back in General 1, you may have been taught about these things called adducts. Like when boron trifluoride, it forms a coordinate covalent bond with ammonia, so it can get its octet. To form this adduct between BF3 and ammonia. But what's going on here is that ammonia is donating electrons to boron. So that would make it a base by the Lewis definition. But here, boron is accepting the electrons. So that would make it an acid. And by the other two definitions, BF3 wouldn't fall under either acid category. There's no protons to donate. And when you put it in water, you don't get H plus or hydronium. I mean, it reacts with water, but you get other stuff. And in some areas of chemistry, you'll see the Lewis definition actually used a lot more. Again, in Gen Chem, the first two work fine, especially the Arrhenius definition. And as we get more into the acid-base chapter, or chapters, depending on what book you're using, you'll see that you might be using the Brønsted-Lowry definition a little more. But in some areas, the Lewis definition is used a lot more. It kind of depends on what you're doing, what you're studying, which definition works best for you. But they all work. They all still work fine. So whatever you're doing. All right, but that'll be it for acids and bases for now. And we might talk about it a little bit more at some other time. But for now, that'll do. Pig. Besides, just because you have a high kill-death ratio in Battlefield 4 doesn't mean you're better than me. I have a PhD in chemistry. Go f*** yourself.